So here's a summary of today's class. We started with a review of what we did last time, which was confidence intervals, in particular a 1 minus alpha times 100% confidence interval. Just notice that if alpha is between 0 and 1, hence a decimal, that 1 minus alpha is also between 0 and 1. If we multiply that by 100, that's a percent. So that's why this funny notation here is just so that when we talk about a 95% confidence interval, alpha is 0.05. So we did an example here. I'll just let you read this on your own, but basically if we're given that the sample mean is 800, then knowing that alpha is 0.05, and the z alpha over 2 is 1.96 we saw last time, giving us our confidence interval. Then we started, we actually backtracked a bit to section 7.31 to derive some of the formulas that we've been using. And I pointed out that the treatment in Rice on pages 205 to 209 is done better, in my opinion, in Pittman, page 441 to 443. So that's the treatment I'm doing here, and I think it's a little bit more elegant. So here I have a population with capital N elements, and x1 to xn has mean mu and variance sigma squared. Perhaps I didn't quite indicate this so well, but these are small xi's. Let me actually rewrite this and make it clear that they're small. Okay, so these are, for example, the annual income of I households in the US. So now let capital X1 to Xn be a simple random sample, where x1 is one of these numbers here, and x2 is another number from there, and so on. And we're picking here without replacement. So you can think of these xi as uniform x1 to x capital N. At this point, I showed you what a great guy I am, and told you that I wrote for you a summary of all the Stat 134 probability that you should know. So this is on B courses. What I think you'll find most handy is just a summary of all the distributions, both discrete and continuous. So in particular, uniform on x1 to xn has this expectation and this standard deviation. So following these formulas as follows, then I introduced t as a sum of these xi's, and we showed that the sample mean is just t over n, and the expectation of the sample mean is the population mean. Now the variance of t, you need to, because the xi's aren't necessarily independent, because we have a simple random sample, we have to introduce covariance here. So I just wrote the variances as a sum of variances and covariances, and I wrote a formula for the covariance of x1, x2, using a clever argument from Pittman, in which he looks at a sample of x1 to x capital N. So that's basically you're just drawing all the tickets in your box and adding them together. So obviously if you draw all the tickets in your box without replacement and add them together, every time you do that, you're going to get the same sum. So the variance will be 0 in that case. And then we can solve for the covariance of x1, x2. And this gives rise to the correction factor term for the variance of the sample mean. We then turned to section 7.3.2, estimation of the population variance. And I just noted to you that if your xi are IID, then the variance of the sample mean is sigma squared over n. If, on the other hand, they're just SRS, then you're going to have this correction factor. I'm being very sloppy with small x and big X. Let me clean that up a bit. So capital X represent random variables. Okay. So now we saw in quotes because I just basically showed you the proof and asked you to read it. So the sample variance is an unbiased estimator of the population variance, which just means that its expectation is sigma squared. And if you look, the main result in chapter 7 is this table on page 214, and you'll see that you'll see right here. You'll see right here that, in fact, this is saying that 1 minus 1 over n s squared is an unbiased estimate of sigma squared. So what does that contradict what we just said? Well, not really. So here x1 to xn is a simple random sample, whereas in the results that we saw before, although I didn't write it, x1 to xn was an IID. So what we need to do next is prove that this factor in front, 1 over 1 minus n, is necessary to have an unbiased estimate in the case where x1 to xn is a simple random sample. So I essentially asked you to figure out what you need to change in the proof, and the places where you need to change are shown in purple here. And I gave you a little bit of time, not enough time, but make sure that you can follow this proof here. I just essentially, so at first I changed the statement. So n minus 1 over n, which is the same as 1 minus 1 over n s squared, is an unbiased estimator of sigma squared. So you need to put the correction factor in here. Let me get another color. So here we need this correction factor here, and then that comes here, and